for commercial building research at the National Renewable Energy Lab. DOE has 17 labs? Something like 17 labs. NREL is in Golden, Colorado. Paul's group is responsible for doing research on new methods and technologies for deep savings in commercial buildings, both in new buildings and retrofit buildings. He's been at NREL at least 16 years, maybe more at this point now. He's an adjunct at the Colorado School of Mines, one of my favorite colleges, and he has a PhD from Purdue. He's a very good speaker. I've heard him several times. So please give him a warm welcome, Paul Torcellini.
Okay, so I have an idea of what's happening here, and I will have to give, I'm going to start with a little disclaimer, right? If I don't make you like a little squirmish in your chair, especially those that, who gets paid to do design, engineering, architecture, okay? So you guys might squirm a little bit, that's okay. It's okay to throw things at me, as long as they're soft, okay? But ask questions, okay? Because a lot of what we think about is process, and how to think through the process of getting low energy buildings built, right? So, we got those that are practicing. Who else do we have here? Architects and engineers that don't practice. Are those the NYSERDA folks? Right? University staff, facilities, right? Okay. How about the rest of you here? Economist. Okay.
Regulators.
I don't know anything about economists. Economy. Regulators. Okay. Good.
Marketing.
Marketing? What kind of marketing?
Oh, all sorts.
All
Right now it's the commercial industrial side of NYSERDA.
All right. Well, and if you can figure out how to market some of this stuff, you know, that is, I mean, on the engineering side, that's one of the challenges we have. In fact, Tom said that I am in Golden, Colorado. I manage a group of about 40 engineers. I'm actually on loan to the US DOE, and I've been kind of sitting in the Washington, D.C. area for about a year and a half. That's going to be wrapping up here in the next 6 months or so. I'm heading back to Golden to be the group manager again. It's been very interesting for the engineer to sit inside Washington and see how some of those things work. And just the different types of people that make the government work, right? And how decisions get made. I don't know if I influence that or not. Maybe I'm too logical, maybe I'm not logical enough, I don't know. So if you're interested in buildings, the whole thing with buildings is, yes, they're important. You know, I mean, that's the first thing to realize, right? We've got a problem with buildings, right? All buildings can be better. All buildings have issues. Even the zero energy buildings we'll talk about have issues. We could make them better, right? And yet a lot of people, you know, the facilities folks say, well, how are your buildings? Well, they're just perfect in every way, right? You know, there's all kinds of things we could fix on, right? And that's kind of that low savings that Tom mentioned, you know, that 5% range, right? 40% of the energy consumption, 72% of the electricity, 55% of the natural gas, split evenly, roughly, between residential and commercial. Now, from my point of view, the definitions and the things we're going to talk about on zero energy buildings apply to both residential and commercial. From my point of view, residential is pretty easy, and you'll see why, right? Pretty low energy densities, lots of roof area to produce it, right? There's really no excuse not to have zero energy houses everywhere, right? Commercial is much harder. A lot of loads, a lot of stuff going on in these buildings. And we're going to concentrate on those, although a lot of the concepts apply to both. Oh, and my little pie chart, right? You want to think about it. A third of the energy goes into buildings, a third of the energy is getting people and stuff to those buildings, and a third of the energy is to make stuff for buildings. And over the last 20 years or so, this percentage has gone down, right? Why? This is in the U.S. Outsourcing, right? That doesn't mean our impact standing here has gone down, right? We've just kind of reached into other people's boundaries, and very conveniently we can just ignore that today, right? And we're going to talk about boundaries. There's some common themes here. One is, where is the boundary? We'll talk about that. But that's just one example of, look at all the good things we've done by saving energy in the industrial sector, and that number's going down. Well, it's somewhat moved the problem someplace else. And we need to remember that. The growth, the last set of numbers we have, and numbers are kind of getting a little old here, but for whatever reason we can't seem to get updated numbers, growing at about 1.6% a year. With the economy the last 3 or 4 years, that has slowed down a little bit. We don't know exactly how much, but it has slowed down a little bit. The growth is faster than energy efficiency measures. That's a big deal. Okay, where's my economist? 1.6% growth rate means a doubling when? I can't tell you that. Oh.
Divided to 70.
Divided into 70 or 69 point something, right? So what is that? Every 30-ish years or so? 35 years? So in 35 years, we have to have twice the electrical infrastructure, distribution system, to power the buildings that we're putting up today. Right? The buildings we put up today, the decisions we're making today, and really this is all about decisions, are mortgaging the energy futures of this country. Why? How long is this building going to be here? Where are our facilities guys? How long do you want this building to be here?
Over 100 years.
Over 100 years. They built a 100-year building. They made decisions that are going to be with us 100 years. You want to figure out how much energy we're going to use in the future? Look at what we're building today and the decisions we're making today. Right? Every decision has an energy impact. Right? In fact, you could actually say every decision has an energy impact. Right? Think about it that way. Right? So, I mean, it could be, Priscilla, the type of coffee you've chosen to drink, the type of cup that you've put that in. Right? All those things have energy and environmental decisions. And in some ways, we need to think about that. Every decision has an energy and environmental impact. Right? And all the players that get involved, right? How you got here today, what you eat, right? What you choose for a career, all those things have impact. Right? And I already said, buildings mortgage the energy futures of this country and the world. Right? That's a big deal. Right? So, kind of with that stage, talk a little bit about some of the stuff that we do at the lab, just as a little background. A lot of it is applied research and development. Right? I don't know anything about little nano thingies. Right? I saw the chart on the wall out there. It said how high I am in nanometers or something. Right? Commercial building energy alliances. What we're doing is working with some of the big market players, Walmart, Target, Whole Foods, Kohl's, saying if they can make decisions in their prototype, they'll look the same, right? Dunk, 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 dunk. They chunk them out, right? If they can make decisions on one building and repeat it many times, that has a big impact. Most people don't realize how well engineered the Walmart store is. Low prices every day. There are reasons for that, right? How much energy do you think the average Walmart store saves compared to code? New construction. Any ideas?
30%.
Yeah, it's somewhere between 30 and 40% below code. New buildings, they're new construction, 100% daylit. During the days, the lights are mostly dimmed or off. Right? They're actually one of the leaders in that area. Target is right behind them. Okay? Not surprising. Right? Because they have to be competitive in that marketplace. Energy is one of the few things they can control. Right? For every dollar for a grocery store, for every dollar worth of stuff they don't have to sell. Or no, let me get that right. For every dollar of energy they save is $40 worth of stuff they don't have to sell. Okay? It's a big deal for these companies. Very small margins, right? Energy becomes one of their profit centers. They have a strong interest in doing some of this stuff. Commercial building, let's see. Partnerships, those are a subset of the Commercial Building Energy Alliance. People that have come to us and said, we want to build a building that uses half the energy. We're willing to build it. We're willing to put that into our prototype. The lab is out there helping them do that, providing some design support, right? And then testing it after the fact. That is now in year about 4 of a 5-year program. We're going to talk about zero energy buildings. Officially on the books is a net zero energy commercial building initiative. Although it's interesting, the last couple of years, if you kind of go searching for that, you don't see a lot of that on the website stuff. That's because the focus actually shifted to renovation, more because of the economics driving the situation. We also put together together technical support documents. How many of you have heard of the ASHRAE Advanced Energy Design Guides? Downloaded about 500,000 of those, just shy of 500,000 of those now. So it was our crew that actually did all the energy analysis, a lot of the writing, working with ASHRAE to get those books out. We do testing out at the lab. We're putting on a brand new $130 million electrical grid test facility out in Golden to look at building to grid interactions. Issues with what happens when you put a lot of PV on the grid. How do you deal with cogen, other pieces, integrating all those things so that the grid can deal with this energy. We'll talk about that a little bit later too. Opti Plus is an optimization program I'll talk about later. It actually sits on top of Energy Plus. How many of you have heard of Energy Plus? Okay, so the core development team is split between some of my staff in Golden and some of the Lawrence Berkeley staff in California. And then also sitting on top of that is Open Studio. Basically, we decided that we could not afford to do front ends, and so we're using what used to be Google SketchUp. It's now owned by Trimble, and we've actually developed modules so that you can download it, and in SketchUp, you can run Energy Plus, kind of sketch up the building in a couple minutes, stretch it, do other things with it, and create an energy simulation model. One of the barriers that we've heard to running simulations is how long it takes to put in the architecture piece, and just the ability to use it. Okay. So that's a little bit of that piece. I think we've talked through those. Okay, so this is Isaac. And his dear father took his puzzle one day and put it together. Right? And at the time, Isaac was 3. And Isaac's like, "No, Daddy, that's not right. There's some problem with the puzzle." Right? Now, if the 3-year-old, or at the time 3, and I guess I'm embarrassed to say that he's now 7, and he probably doesn't like it that I keep showing this picture, but I do, because it works. And what's the problem with the puzzle? Right? The first thing that's amazing to me is that I could take the puzzle and put it together wrong. Right? I mean, Florida is kind of up in the middle, and there's definitely a problem down here. Right? But it's interesting that how many times do we make design decisions, other decisions, really not paying any attention to how the pieces really will fit together? Kind of the big picture. Say, well, the piece fit together, the problem is solved. On to the next problem. Right? Really, design is about making all these decisions. And how do we motivate and influence those decision makers? All of you are decision makers in some way. Right? How are you influenced? Now, this is the engineer talking, right? I mean, back to, I'm not sure I know much about economics, right? I'm certainly not sure I know much about human behavior, right? And yet, isn't that what a lot of design is about? Is thinking through those pieces? How do we work with all those decision makers? And that's everybody. All those pieces that fit together. So, as we think about it, we say, well, kind of a lofty goal with these zero energy buildings, right? And we'll talk a little bit more, but conceptually you think about it and say, well, that 40% of the energy pie, if we could just get rid of that piece of the pie, wouldn't that be great from an energy point of view, right? Well, a lot of people have been thinking about that. ASHRAE's been thinking about it, AIA's been thinking about it, California Public Utility has a zero energy action plan. I guess I didn't do my homework to know what's happening in is there an action plan or dialogue about this in New York?
There's dialogue, no way.
Okay. Where people have actually written things down. There's a federal order that says federal buildings have to be zero energy by 2030. Now it's interesting, this kind of is where policy meets science. People have written all this stuff down and said we're going to do it. 2 problems have come up. Right? The first problem is what? Is this even possible? I mean, nothing like setting policy, direction and policy goal and not having it be achievable. Has that ever happened before? Never, right? A good policy person right here. Right? So that's, one of the problems is it even possible? And so, and the other is what is it? Right? We'll talk a little bit about what is it here as we go through this. And so we actually were charged as a national lab to answer those questions. Okay? And this happened 5 or 6 years ago. And so one of the things we said, well, is it possible? So here's where we are today. Right? If we took, and we take buildings and we build them, you know, and some of them have been around for a long time, so you take the entire building stock, we're currently sitting at about 90,000 BTUs per square foot. And again, we're embarrassed to say that the latest numbers we have on that from the Energy Information Administration is 2003, right? And there's a whole set of politics that goes with why we don't have anything newer than 2003, but it is, well, push comes to shove, they probably haven't changed much, but we'll just say that's where we are. And if we're off a little bit, it doesn't really matter. Right? If we leveled all those buildings, now, in some ways it was an opportunity. Greensburg, Kansas, a couple of years ago had a big hurricane, wiped out 97-ish% of the town. And they had an opportunity to rebuild. And so one of the things they did was they did engage with us and said, how can Greensburg become Green Town? Right? And really engage in putting pieces together to become a green community. Right? And they set some goals and they went after it. Well, they did a whole lot better than this, but if we leveled all the buildings and rebuilt them, we could drop that number about 20% from where we are today. Okay? So now, here's where the kind of the magic came in. We started doing some energy simulations, and we said, can we model the U.S. building stock? We actually took and modeled about 5,500 buildings, moved them around, and said, what is possible? What things can I do to buildings to make them more energy efficient? Right? I can put in better glass, I can put in better heating and cooling systems, I can put in more efficient lights, I can start daylighting anything that's close to a perimeter. Right? All these things I can do. We call that the max tech building. Well, I can drop that number in half. Right? And so Tom kind of talked about, you know, kind of deep savings and new construction. You know, it's interesting that our simulations line up pretty closely to this vision of people saying we should be able to cut building energy use in half. Now, and this is current technologies. This isn't anything new. If I took those buildings and covered half of the roof area with photovoltaics, I could drop that number another 75%. Now, why half? Well, you ever looked on the rooftop of a commercial building? Right? There's all this other stuff up there. Right? And so as we actually took Google Maps and started looking around and did surveys of buildings, and half was about the right number. Okay? So that's a pretty substantial difference. It's not zero, but I think that Tom would be happy, and the NYSERDA staff would probably be happy if we could go from 90 down to 12. Okay? And maybe we'll talk a little bit more about why we're not there. Now, we had done some studies on actually going out and measuring some buildings. These were kind of high-profile buildings now about a decade ago that were out there. Oberlin College Environmental Studies Building, Chesapeake Bay Foundation, what's their claim to fame for buildings? Anybody know? It was the first LEED Platinum building. Okay. Zion National Park Visitor Center. What else is up there? Cambria Office Building is in Pennsylvania. The thermal test facility was built on our campus in Golden, Colorado. I forget who there. Anyhow, when you look at those buildings, they're all kind of right in this max tech area. Right? And so that's saying, well, maybe the study wasn't that far off. This was kind of, if we really push the envelope and work hard, this is where we can get to. Right? Some interesting stories on here. Zion National Park. Right? That building was designed at 80% energy savings. Now, one of the things that we hear about is, guess what? It's designed 80%, right? Do you think it operates at 80% savings? Right? Even a building that was designed at 30%, what does it usually operate at? Maybe 15, right? Buildings never do quite as well as you 70% savings. The building costs 30% less to build than a conventional visitor center for the Park Service. Why was that? There's no mechanical system. Where are my mechanical engineers over here? Sorry, guys. Now I have to disclose, I am a mechanical engineer, right? But we got rid of the fuel storage, we got rid of the mechanical room, we got rid of all the ductwork. The building basically heats and cools itself with the envelope. Right? So question?
The max tech scenario, the models, were those retrofits of existing sort of structures and envelopes?
So what we did was we took the data out of CBEX buildings, right? And we had an algorithm to basically create that building, apply a set of rules to it based on the date of construction. Okay? So if it was built in 2003, we would assume, current ASHRAE code. Right? If it was built in 1977, there was a whole other set of rules that got applied to it. And we ran those buildings. And then we correlated that back to the CBEX. And we're within a couple of percent. So we basically created a model of 5,000 buildings that mimicked CBEX. Once I had that, I could then globally apply strategies, right? Pull out all the inefficient HVAC system and fix the HVAC system. Get rid of all the T8s or T12s and replace them with T8 lamps, right? Anything on a perimeter, replace it with daylighting strategies. Add insulation to the roof deck, those kinds of things. Yes?
So there's a couple of things with a lot of numbers and a lot of data. It's eating ground for room though. There's a standard deviation within that 90. There's building types within the